I'm done, finally. This video marks the end of my video series about programming an embedded system from scratch. 28 videos later, and I've gone through how to set up a makefile, version control with Git, setting up a CI, creating a software architecture, writing drivers for things such as GPIO, UART, ADC, motor control, and I2C, how to think about microcontroller memory and interrupts, how to do board bring up, implement a state machine, and even simulation. In essence, how to bring an entire project together in a logical and structured way. My goal was to document the entire process to end up with something that can be seen as an educational example for anyone who wants to get into embedded systems development. I wanted to do an entire project because some aspects of embedded development is easier to learn and understand in the context of an entire project. And there also doesn't exist that much content like this out there for obvious reasons, I realize now, because it's a gigantic effort to document everything like I've done in this video series. And I want to use this last video to reflect a little bit about this project. First of all, and I think I've said it before, what I've done here should not be looked upon as best practices on how to do things. While I've obviously put more rigor into this project than your typical hobby project, I've still taken shortcuts, and some of the things I've done here I wouldn't have gotten away with in a more professional setting. For example, one of the things I've done in this project is to write all of the code from scratch, all of the drivers down to the register level. And in modern development, that's actually something you would like to avoid, because you want to try to reuse existing code, whether that comes from a previous project, existing libraries, or code from vendors, and so on, because it's time consuming and kind of stupid to re-implement code if it already exists. With that said, bare metal programming still has its place, even in modern development, because every project is unique, so you are going to have to maybe not write all of the code from scratch, but there are going to be existing code that you have to modify and adapt to your specific application. And in that case, you often still end up having to work at a low level. And in those cases, you still need to understand bare metal programming and how things work at the register level. And I also think that from a learning point of view, bare metal programming is crucial to understand the fundamentals, and it's where you should start before you move on to take advantage of all the existing tools, libraries, and code, operating systems, and whatnot that exist these days. So in hindsight, educational wise, I'm quite glad I did everything from scratch in this project, because it gave me an opportunity to actually show how things work, especially some of the important peripherals that you need to understand as an embedded systems engineer. And bare metal programming reveals that there is no magic behind anything. At the deep level, it's just register writes, and then you layer code on top in order to make it easier to work with and understand as a human. Then regarding the project itself, there is of course other things that I wish I would have done differently, as there are with any project that you do. One of the things that I'm not satisfied with is kind of the end result of this robot and how it performs. And there are mainly two reasons for the bad performance, I think. One is the mechanical design. When I designed this, I had a big focus on cramming in as much as possible. I believe that having 4 motors and 4 wheels would give me more power. And yes, it does, but it also makes the driving behavior a bit more wobbly and not as stable as it should be. And I think I would have just have a better development experience and behavior if I decided to have 2 motors instead of 4, maybe have 2 bigger motors. And similarly, I think I should have gone with fewer and simpler sensors, especially the range sensors. I decided to have 3 range sensors in the front and 1 on either side, and I ended up having to discard the sensors on the side because they didn't, like the placement I did of them didn't really work very well. I had a lot of false detections, and I realized that they are not really that beneficial. Also, they are quite complicated, and it took a lot of effort to write the drivers for them. And while they are able to detect the enemy at a close and far distance, they are too slow at sampling this distance. And this is also true for the line sensors in the bottom here. They are not giving me samples fast enough, which heavily limits the reaction time of my robot and how fast it can drive. Because in the end, I think that the sumo robot that's going to win is the one that reacts the fastest. So the takeaway here is to try to go for a simpler design. And then as for the other parts, I should have picked another microcontroller. This microcontroller is good for teaching and learning about embedded systems, but it's not very suitable for this project. It doesn't have the kind of peripherals that you need for a motorized project like this. One of the main things that indicates this is that it doesn't have dedicated PWMs. And I ended up having to fight for the timer peripheral to get all the functionality that I needed. Another thing is the flash memory and RAM available on this microcontroller. If you saw my previous video, I actually ran out of flash memory in the end, and I had to compile out things in order to fit the functionality that I needed. And yes, for embedded systems development, you should of course always think about how much space your code occupies. That's just good practice. And picking a smaller microcontroller can be a way to force you to learn about this. But I also think that if I would have just went with a microcontroller with double the amount of space, it would have made my life a bit easier. Because for a one-off hobby project like this one, there are so many factors that doesn't matter in the choice of a microcontroller. Normally you have to think about the cost, how much power it consumes, and a lot of other things. But in this case, if you're just gonna buy a single microcontroller, whether it costs $1 or $5 doesn't really matter. And with this in mind, there would have been so many other more powerful microcontrollers that I could have picked instead, that would have made this project better and easier to develop. And lastly, I got a bit carried away with the simulation in this project. Yes, it was a good lesson in C++ programming to write my own simulator from scratch, but the effort wasn't really comparable to the benefit it gave me in the end. I should have just done something simpler, maybe written up something in Python, or skipped the simulation altogether and done everything on target, even if that would have been more of a hassle. With this video series behind me, what's next? Well, I want to continue making project-related embedded systems videos. While this marks the end of this video series, it's the beginning of this YouTube channel. And I'm already working on another project, and I have some ideas for a video. But it's not going to be another video series of this magnitude. But other than that, I don't know, and I will have to see how things turn out. Anyway, that's all for now. Thank you for watching my video series.